Okay, hello everyone. Please sit, we want to start. Welcome to the session on Byzantine Agreement. Our next speaker is Daniel Collins, who's going to talk about efficient crypto-agnostic Byzantine Agreement. Please go ahead.
Let's see. Hello, everyone. Thanks for coming. So today I'll be presenting on Juggernaut, crypto-agnostic Byzantine Agreement. So this is joint work with Yuval and Jovan, and I wanted to particularly thank Yuval and also Joseph Jaeger for help with the slides. Good. So today's session is on Byzantine Agreement. So the problem statement is basically as follows. We have n parties, P1 to Pn. They each have input of VI. So we bound the number of parties that are malicious. We use the number T. And we assume that the parties have authenticated channels between each other. So I guess the real difficulty here is that the parties have like pairwise channels, but they don't have some kind of broadcast channel or something like that. And so the difficulty is to solve some distributed problem. In this case, it's going to be consensus. So here's kind of a diagram of what the network looks like. The properties of Byzantine Agreement are as follows. So we have the agreement property, which says that all honest parties, as I said, they have this input VI, they all output the same value. Now validity is stated as follows. If all honest parties input a value V, then V is the only value that can possibly be output by honest parties. And finally, we have termination, which basically says that all parties will eventually terminate. And to sort of motivate this paper, we note that if you have like n equals T is the number of malicious parties, it's impossible to solve. So we restrict T in some way. So the question is how do we restrict T? Well, this depends on what kind of assumptions we make about the adversary. So we assume first, so in sort of one setting we have, which is what we call the authenticated setting, if we have some public key infrastructure that can be set up, and in this case, if we assume here that the adversary is computationally bounded, so basically everyone uses the PKI to basically share, like they upload like their signature public key. Well, here we can assume that the number of faulty parties is at most n over 2, or strictly less than n over 2. So this is a good case. In practice, we want to, ideally, we want to use a protocol that has sort of, that supports as many corrupted parties as possible. But indeed, this is not always possible depending on the assumptions. So in the sabotage case, which is sort of which is a bad case, we assume that sort of the setup can be compromised. So that is to say, if you have some public key infrastructure, the secrets can be known to the adversary. And indeed here, the adversary can be unbounded, sort of computationally. And indeed in this setting, at most, we assume at most a third of the parties can be corrupted. And these two bounds are sort of proven to be optimal. And indeed, sort of there are many works and sort of consensus on these two settings, sort of protocols with various performance characteristics in this setting. And there's indeed been like decades of research. But as a protocol designer, the question is really which setting should the protocol designer choose? So of course, the authenticated setting is good because you can support more corrupted parties. But in practice, the public key infrastructure, somehow you can imagine it as like a trusted third party. So this is something that you have to set up. This can not always easily be set up. This may not be something that is sort of, this may break, this assumption may break. And moreover, if you're using signatures to build consensus, the cryptography may be broken. I mean, we have all this research on post-quantum crypto and stuff like that. And in particular, in these protocols, they will typically have some kind of like equivocation check where sort of parties will, and sort of in these protocols, these checks fail, and even if the cryptography doesn't work, then even if you have like one malicious party, then these protocols will break. So this is bad. And then on the contrary, we have what we call sabotage, this sabotage world. So in this case, as I mentioned, the number of corruptions is going to be less that you can support. So this is going to be at most a third rather than half. And sort of this difference, this distinction could be quite significant in practice. And indeed, what we call sort of a quorum intersection argument will fail in these protocols if the number of corruptions is going to be larger than this third. So of course, if we have a protocol that's secure in this sabotage world, we can run a protocol in sort of this authenticated world. But we have to trade on sort of this corruptions, which is not ideal. So the question is, can we build a protocol that somehow is adaptive to or sort of agnostic to the setting in which we're in? So this, what we call here, is crypto-agnostic Byzantine Agreement. So this has been studied before by Fitzy et al., so in 2004. So what they note, firstly, is that sort of if you have this optimal threshold of corruptions in both cases, then the problem is impossible to solve. But in fact, they showed that if you have this sort of bound on the number of corruptions in between the two worlds, so they state this as a plus 2s less than n, then it is possible indeed to solve this problem. So a nice choice of these parameters is that if you have sort of the optimal number of corruptions in the authenticated setting, then you can essentially have at most a quarter of the number of parties corrupted in the so-called sabotage setting, essentially for free. And so in terms of resilience, this is for free, which is nice. Basically, you can run this authenticated protocol, and then you can have sort of also have these guarantees in case public infrastructure or crypto breaks. Indeed, so there's basically two works that looked at this problem before, but the problem is that, at least sort of in terms of practicality, there's a nice feasibility result, but the problem is that these protocols that were implemented in the past are expensive, so they're concrete protocols, basically, in particular the communications are roughly quartic in number of parties, and the round complexity, basically they build broadcast protocols in order to build MPC, but these protocols are not optimized. And so the question is, I mean, if you want to have a protocol in practice that provides sort of guarantees in this setting, then the deployers are essentially, until this talk, are stuck with these guarantees. So this kind of motivates the paper, sort of how efficiently can we solve this problem? And this indeed is the sort of what we solve. So the main result is if we have two protocols, sort of we take like a protocol that's that works in both of these settings, one protocol per setting. Basically, what we show is that we can sort of build an efficient compiler that will output a protocol that is sort of that works in this what we call crypto-agnostic setting. So what are the properties of this compiler, or when you instantiate this compiler with specific protocols, which we'll talk about a little bit? What do we get? So we get this optimal resilience. We get sort of a quadratic additive communication overhead, where we have lambda n squared, lambda being the security parameter, sort of in the communication, which for adaptively secure protocols, this is more or less optimal, which is good. And the compiler is nice because it also preserves many nice properties of the underlying protocols. So, for example, if you have two protocols that are more or less deterministic, modular the fact you're using a signature scheme, or if the sort of authenticated protocol is early stopping or has sort of expected constant round complexity, then the overall compiler will also sort of preserve this property. So in this sense, we sort of optimize for this authenticated setting. So how do we build such a thing? So a first natural question is, okay, we have these two protocols. Why don't we sort of run one of them and then run the other one with basically using the output from the first one as the input to the next one, and then maybe outputting from the second protocol. So this is more or less what this would look like. So in this case, we run the authenticated protocol. We output some value. So this is the perspective of some particular party, but basically every party will sort of have, like, from their local perspective, will have a view like this. And then, yeah, so they will input their output value from the first one to the second protocol, and then they'll output some value, and that will be the output. And so, yeah, we assume right now that sort of the runtime of each of these Byzantine Agreement protocols is sort of something that is bounded. So then parties in particular can all start this second protocol at the same time. So the main problem, of course, is that this doesn't work in our setting. So the problem is it's insecure. So recall that the adversary is able to sort of work in either one of these two worlds that we sort of, so we assume at the beginning sort of time that either the adversary is in this sort of authenticated world or in this sabotage world. So basically, if we run for example, here, if we run the authenticated protocol first, if the adversary is in fact sort of running in the sabotage world, then basically the Byzantine Agreement protocol in the first case does not provide any guarantees. So in particular, if we have something like validity where all parties must input the same value, if all parties input the same value, then the output is the value that was input by honest parties. This will basically be not provided by this protocol. So the output of this authenticated protocol can be arbitrary in the case that and then that will sort of feed to the second protocol, and ultimately, you don't have security. Likewise, in the second case, if you're in the authenticated world, the first protocol may provide some guarantees, but then we can basically assume that the second protocol provides no guarantees. So maybe one natural direction is, can we somehow sanitize the inputs to each of these protocols? such that we can still provide some guarantees. So this sort of motivates the definition of the use of graded consensus. This is sort of a relaxation of the Byzantine Agreement problem. Instead of parties outputting a single value, they will now output a pair of values, the second pair in the tuple being, the second value in the tuple being this grade. In this case, we have a binary grade, which is either 0 or 1. And the guarantees are roughly as follows. So rather than now all parties outputting the exact same value, in the case of validity, parties will output a value v1. So 1 basically means that the sort of is a sort of confidence, a high confidence in the value. But the important thing is the consistency property here is that if sort of any honest party will output a value like with a grade at 1, then it means that all honest parties will output that value, but with a grade that's either 0 or 1. So in particular, okay, so in this case, if no party outputs 1, then the values that are output by honest parties can be different. But as long as you have one party that outputs a grade 1, all parties will agree on the value, even if they don't agree on the grade. So that's sort of what we have. And we know that we can do this rather efficiently, in particular with sort of quadratic communication in constant number of rounds. So we have some protocols from the literature that we can use. So the question is this enough for our case? So I guess indeed it's not. So this is more or less what the setup would look like, or the way we can sort of towards the protocol we construct. The problem is we still have the same problem as before, because we're in this case we're running sort of the authenticated protocols, and then we're running the sabotage protocols. So indeed, if we are in the sabotage world, the authenticated protocols will provide no guarantees, and then yeah, basically that. Even though the latter protocols may be secure, we still we don't inherit. We sort of don't have any guarantees from the first protocols. So the question is really, can we make this secure? And a very natural way to do that, which has been done sort of particularly in the network, the so-called network agnostic setting, is to provide these graded consensus protocols with additional guarantees. So in particular, we note that the protocols only have guarantees in their respective worlds. But what we do is we come up with graded consensus protocols that provide guarantees in both worlds. And this is sort of how we're able to get a secure protocol. So in particular, we introduce something with extended validity. So now instead of parties so if all parties input some value, honest parties input some value, all parties will output the value and corresponding grade 1. Now what we want is that this guarantee is provided for both of our graded consensus protocols in both worlds, so in the authenticated world and the sabotage world. So this is really the sort of the bridge that gets us to something that works. And what we show in this work that is basically we can build two graded consensus protocols that provide guarantees in both worlds. Nice thing is, relative to the sort of, if we assume some black box graded consensus protocol, we can build this with some quadratic communication overhead, relative to the additive communication overhead. So, for example, we have the protocol GC-SAB star, which is basically a graded consensus protocol that works in the sabotage world that additionally provides validity in the authenticated case. So in this particular case, the protocol basically has a three-round overhead over sort of whatever black box protocol we use, and conversely, likewise in the other case. And so these protocols provide nice guarantees. So this basically leads us to how the compiler is constructed. So here's what it looks like. Rather before we had a graded consensus protocol in the authenticated case. Now we have a graded consensus protocol in the authenticated case that also provides extended validity. And basically, we feed sort of the outputs of protocols to the next protocol instantiation. So let's look at some properties. So the first one we consider is sort of agreement in the sabotage case. So indeed, we do provide this because basically everything that comes before doesn't really matter, let's say, but then all sort of, at the end, we have this sort of Byzantine Agreement protocol that works in the sabotage world, so we can inherit the sort of agreement property from that protocol. And so basically we have that for free. The question is, though, do we have validity in this case? So recall, validity is that if all honest parties input the same value, then that is the only value that can be output. So as written, we do not have this yet, because if we run this authenticated protocol, this Byzantine Agreement authenticated, the protocol, Byzantine Agreement protocol that works in the authenticated case, that can essentially be like the output of that protocol can be arbitrary, so it can basically ruin the validity property. But in order to get around this, what we'll basically do is that we'll sort of overwrite the output of this protocol. So the main insight here is that so if we're in the authenticated world, what we can basically do is just run the protocols that work in the authenticated setting, and then sort of somehow in an optimistic case, we can basically skip running the other protocols. So in particular, what we do is that, so we start firstly by running this graded consensus protocol in the authenticated world with this extended validity property. We then run the Byzantine Agreement protocol. And then after this Byzantine Agreement protocol, we basically check whether the grade from the original protocol is 1. If it is, then we basically replace the output of the original of the Byzantine Agreement protocol in the authenticated case with the output from the graded consensus protocol. And as I'll talk about in a bit, we also sort of don't execute the rest of the compiler. But the problem here now is that we don't have any authenticated properties, or properties in the authenticated setting, because the adversary can do whatever they want to basically ruin the protocol execution in this case. So then, sort of what I alluded to just then was that we can indeed bypass this, and very quickly sketching how it would work. We basically, once parties finish executing this authenticated Byzantine Agreement protocol, they will sort of they will multicast to everyone the fact that they have finished this protocol with a signed value that they have sort of output. And then basically, if a sufficiently large number of parties receive this message, they will decide value. Otherwise, we have some extra logic that basically will work out whether or not parties should decide or not based on these messages. Yeah, so one thing to note is the protocol, like I mentioned before, is that indeed, if we have we're in this case where sort of parties do not have to execute this sort of latter two protocols, then the parties will the protocols will preserve some nice guarantees from the authenticated case. For example, the fact that the original protocol may be early stopping, the Byzantine Agreement protocol. But one problem here is that the Byzantine Agreement protocols in the early stopping case or the randomized case, sort of necessarily, the parties cannot output a value in the same round. And yeah, so what that means is if they output some value in the authenticated Byzantine Agreement case, they will then start the next protocol in different rounds. We assume that parties start all protocols in the same round, so this is a problem. What we can do is basically we introduce this well-known technique, what we call a synchronizer, is that parties can basically sort of get around this problem. Yeah, I'm going to go into that because of time. So then, okay, so we have that. Let's say that works, good. So then we have this protocol, this sort of compiler that is black box in the underlying choice of the Byzantine Agreement. So let's maybe plug into protocols and see how it looks. So the usual the metrics of complexity are communication around complexity in consensus. So we have two sort of main variants that we consider. The first is sort of the deterministic case, let's say, where sort of if we plug in sort of the state-of-the-art protocols, we have sort of this quadratic communication complexity in the sort of authenticated world, and then the number of rounds is going to be, in this case, it's going to be OF, where F is the number of actually corrupted parties. But then in the sabotage world, the number of rounds can be n. And then in the randomized case, if we plug in the state-of-the-art, again, we have this quadratic communication complexity, and the nice thing here is now we can have expected constant round complexity, but then the communication will blow up a bit in the sabotage case. So one of the natural problems is, one of the natural questions for future work is, can we sort of improve this sort of complexity in the sabotage case? And so yeah, that's the end of the talk. Thank you.
Thank you, Daniel.
No problem.
Questions? Anyone has any questions? Speaker?
Maybe I missed it, but how does termination preserved when one of these intermediate stages just doesn't terminate?
Okay, good. So basically we have, we assume in the paper that the number of rounds that the gap between the number of rounds that honest parties will terminate is 1. So let's say we have this property, and then what we do is basically at the end of this protocol execution, a party that decides will basically multicast the fact that they've decided with a signature attached to it. So then if sufficiently many number of parties will sort of receive a value of this kind, which is going to be n minus a, which a is the number of the corruption bound on the number of parties that in the authenticated case, then parties will decide. But then what they can do is then multicast this value to everyone else. So then if the first honest party decides, after having this number of values, then they can multicast this message, and then all other parties will receive this message in the next round. And then what we do is, so we have this, so this will work in sort of both worlds. And then what we basically do is in the latter two protocols, parties will execute in sort of, they'll execute the protocols, but one round will sort of take like 2 or 3 rounds. So they'll sort of like slowly execute the protocol to synchronize the rounds. So yeah, we can talk about this offline, but the time is.
Okay, let's thank the speaker again. Our next speaker is Victor Shoup, and he's going to talk about minicasts, minimizing the communication complexity of reliable broadcasts.
Okay, thanks. So this is joint work with Thomas Locher. Okay, so this talk is about reliable broadcast, which is a very different problem than what was talked about in the last talk. So as there, we have N parties. They're connected by authenticated point-to-point channels. But what's different here is that the communication is completely asynchronous, so there's no bound on the time it takes to deliver messages. And it's controlled by the adversary, who can control the order in which messages are delivered. We assume that that the number of corrupt parties is at most t, and that this is strictly less than n over 3. This is you can't really do any better than this. And these corrupt parties are completely Byzantine. They can do whatever they want. One of these parties is the designated sender for one instance of the protocol. And the protocol should allow the sender S to broadcast a single message M to all the parties. And the properties are correctness. All honest parties that output a message should output the same message. And if the sender is honest, then that message should be the one that the sender wanted to send and not some other message. Completeness says that, so even though, this is always kind of weird, even though we're in an asynchronous network and the adversary can choose to deliver messages in any order, or maybe even choose not to deliver messages at all, but if any party outputs a message, or the sender, or an honest sender inputs a message, then eventually all honest parties output a message. And the eventually here is doing a lot of work in the sentence, because the adversary doesn't have to deliver messages, but to the extent that he gets around to eventually delivering all of the messages that he's supposed to, then the honest party should output something. So let's talk about complexity. So you can talk about message complexity. This is the total number of messages sent from all honest parties to any other party. The study of reliable broadcast goes way back to the 80s with a paper by Bracha. This is the classic protocol that most everybody probably has seen at one point or another here. This has quadratic message complexity. More interesting, though, and what I want to focus on here is the communication complexity. This is the total number of bits in aggregate sent from all honest parties to any other party. So we're counting the number of bits transmitted by each party and adding them up. Bracha, unfortunately, it's a nice simple protocol, but its complexity kind of degrades. The communication complexity is pretty bad when n gets big. So it's the length of the message times n squared. So that's not so great for large n. The first work in this area that really worked to improve this complexity was by Kashan and Cicero. So this has complexity, does this work? Yeah. It has a complexity message length times n, plus another term, lambda times n squared times log n. Here, this lambda is the hash, the length of the output length of a collision-resistant hash function. So for very long messages, say n is maybe up to 100 and m is like a megabyte, this is going to be the dominant term here. And so in that regime, this is going to perform a lot better than, say, Bracha. There's been a lot of work since then. So more recently, Das, Zheng, and Ren looked at improving the communication complexity in this case, but they looked at this term. So this is interesting in the case where m is small to moderately sized, the length of the message is small, so it's interesting in that case, but not so interesting in the case where m is, like I said, a megabyte or so, and n is like up to 100 or so, then this doesn't really help. More recently in this area, Abraham and Asharov looked at this problem, and they noticed that you can achieve up to constants the same result as this, but where you don't need a collision-resistant hash function. You just can do its statistical security. And I became aware last night there's more work in this space that I should mention that even gets rid of the statistical security stuff and can de-randomize this. And I didn't put it in my slide here. But getting back to my original spiel here, that for large messages, this stuff is this stuff is nice, but for large messages, it's not very helpful, right? So for large messages, we should really worry about these big O constants, the constant on this term. Now, one other aside I should mention here is that this is kind of optimal in the sense that if we're going to just deliver the data to every party has to receive at least length of m bits. So somebody has to send those bits. So this is the communication complexity is going to be at least a constant times m times n. In all of the above papers here and everything in the literature up until just very recently, this constant happened to be 3. And should we worry about constants? Well, probably. I mean, for applications like, think about blockchain applications where you have a single sender, a single sequencer, that's the buzzword they use these days, a sequencer sending out blocks to all the parties. And these blocks, and people are like very obsessed about getting very high throughput, hundreds of thousands of transactions per second. And so these blocks are easily going to be in the megabyte range. So you have this poor sequencer sending out the same block to hundreds of parties, and if it's just running over ordinary, TCP channels, he's literally going to be sending this megabyte block to this guy, and then also to this guy and this guy and this guy. There's no, in the real world of wide area networks, there's no magic broadcast that you can use. You just have to literally duplicate all of the work if you do it that way. And that's the way most of these things work. But if you, and the sender, the sequencer, can easily become a bottleneck, and this has been analyzed in a number of papers that have done empirical experiments, and they've shown that as n starts to reach the dozens up to 100, just the whole thing, latency doesn't even matter anymore. It's just the bandwidth limitation that's causing you to saturate the network. And so so if you can improve this constant for protocols like this, then you just will get an improvement in throughput proportional to any improvement in that constant. So it's a real world concern. So like I said, all of these protocols had a blow-up of kind of 3. Last year, my co-author, Thomas Locher, kind of was the first person to even ask this question. Like, this 3 had been floating around for so many years that everybody thought it was like, a constant of nature that was just there, and never thought to say, well, is this actually like the optimal constant? So he brought the constant down to 2. And then in this work, we bring it down to 1.5. And in some sense, it's optimal. I won't go into you have to restrict the model in certain ways. And in certain sense, you can't do better than 1.5. So that's our work. And this is all we're using hash functions to do this. And so we have the same kind of second order term here that appears like in Kashan and Tesaro when we're using Merkle trees and so on. There may be a way to improve this term and maybe make it statistically secure as well without hash functions. That would be an interesting problem, but not the one I'm looking at here. Okay. So let me talk about where this 3x blow-up even comes from, and then give a hint as to how we improve it. So in the pre-Locher era, everybody uses an n, n minus 2t erasure code. So this means we take our message and we encode it using, read solemn or some such as a vector of fragments, f1 through fn. And the parameter n minus 2t here means that we can take any n minus 2t fragments to recover m. So fragments, if t is around n over 3, and we have this recovery here, so each fragment will be about 3 times the message length divided by n. And so the idea, how all these protocols kind of work as follows. So the sender encodes m as a vector of fragments like this, and the sender is just going to send each party its own fragment. So it sends pi, the fragment fi. And I'm not going to, and let's actually, this is the complete protocol that I'm going to show you if you assume that everybody is honest. Maybe they crash, but they don't send the wrong message. And then by throwing Merkle trees and whatnot at it, you can kind of constrain correct behavior. But just the dissemination of the data is the challenge here. So let's not worry about even correctness here, except for maybe crashing parties. So once each party pi receives its message, its fragment, it'll broadcast it. Each party then outputs the message when it receives sufficiently many fragments, and it receives a message from at least n minus t parties that tell it they're holding fragments. So it's got to have confirmation from n minus t parties as holding fragments. Why n minus t? Because we're in the asynchronous setting, so you can never really wait for more than n minus t messages from anybody. Why n minus 2t? Because out of these n minus t parties, t of them might be lying to you, and they're not holding fragments. Or they are, but they're not going to broadcast them to anybody else. So there's really only n minus 2t fragments out there that you can rely on. So to maintain completeness, right? So if I'm going to output m, I only want to output m if I'm sure that everybody else will eventually output m. So I got to be sure that there's at least n minus 2t good guys out there. They're going to broadcast their fragments so that everybody else can also output m. So that's kind of the basic idea. And that's where the constant 3 comes from. So, okay. So now we want to reduce this blowup of 3. How can we do that? Well, we can use an erasure code with a higher reconstruction threshold. I mean, there are n minus t honest parties, so morally speaking, there should be a way to just have a reconstruction threshold of n minus t. I don't know. It just feels like it should be doable, right? So, and then if we do that, then each fragment, if you look at this, then each fragment with this higher reconstruction threshold would actually have smaller size, like 1.5 times message length divided by n. So we could, in principle, get the blowup down to 1.5 if we can use an erasure code like this. But the problem is how to maintain completeness. Because in the previous slide, I showed you that if you kind of follow the recipe that's been used over the years, this isn't going to work. You can't use a reconstruction threshold this high because you can't be sure that there's going to be that many parties out there who are going to be broadcasting the fragments that everybody's going to need. So Locher, in his original work in 24, where he raised this question, he does use an n minus t erasure code with a higher reconstruction threshold, but the technique he uses to maintain completeness requires parties to broadcast a little bit more information than they really should have to, and you get or than you would hope to. And so his protocol pushes the blow-up factor from 1.5 back up to 2. It's better than 3, but not kind of down where we think it should be. So this work, I have 1 minute to tell you what the whole idea of the protocol is very briefly. We use the same high threshold reconstruction for fragments, but then we also employ a trick which appears in different guises in the MPC literature in different applications, but we use it here kind of in a slightly new way, maybe kind of sort of new. We take each fragment and we encode it. We apply an erasure code to each fragment. So each fragment gets cut up into little pieces. Those little pieces, though, can be recombined using using the lower threshold of n minus 2t. So in this way, we can, and this is the hand-wavy part. So using these mini fragments, it's possible to arrange with some careful logic and how you send everything out to arrange that the honest parties can help you. You don't rely on the sender to send you necessarily your fragment. You can rely on your friends to send you mini fragments that will allow you to obtain your fragment And because these mini fragments are so small, it costs almost nothing from a communication complexity point of view. So that's my 1 minute, very hand-wavy idea. So some other features and follow-up work. Importantly for applications, the communication is where am I at, Gilad? The communication is very well balanced. Each party, including the sender, by the way, transmits just 1.5 times message length times n bits. And including the sender is very, very important for these kind of asymmetric applications like blockchain, where you have a sequencer who's sending everything out. So he's just going to send the bare minimum it takes out to everybody else, and everybody else can talk to and at that point, everybody else can just talk to each other, and the sequencer or sender is out of the loop. And they're all going to broadcast 1.5 mn bits. And that's very well balanced, and the balance is important because you need to have that in order to not run into this bandwidth bottleneck that can be such a problem. So I already mentioned why that's important. Also, some of you might be saying, yeah, these erasure codes, they're cool and everything, but are they really practical? They're probably like the computational complexity is going to be so high that you're not going to be able to do this. Well, turns out it's not a problem at all. It's insignificant compared to, say, typical network speeds. You can encode and decode stuff faster than your network can upload and decode stuff. And why? And I didn't even know that this was true until I started digging into this a couple of years ago. Erasure coding algorithms, just the theoretical algorithms themselves, have gone through a number of key improvements over the years. And then also over the last couple of years, thanks to the beauty of GitHub and free software, there's been a lot of iterating on improving the implementations of these things. So now it's just not a problem. And if you're interested, you can look at our paper where we talk about benchmarking, and in particular, this library is kind of state of the art. It's really fast. Problem with our protocol, the good case round complexity when the sender is honest is actually 4, which is kind of horrible. Braca is just 3. There are other protocols in the literature that have just 2 if you can use signatures or threshold signatures. But it can be adapted to blockchain-like protocols to have an effective round complexity of just 2, basically, in practice. That's with a lot of caveats and whatnot, but you can shoehorn the basic logic of our protocol into a blockchain-style protocol, and in the good case, when the leader is honest, you can just, the complexity is just 2, and so you can get the optimal latency and kind of optimal bandwidth as well. And then in follow-up work, which we just posted on ePrint a few days ago, we actually showed how to reduce the round complexity to just 3 in the general case, and sometimes even just 2 with threshold signatures and some other technical caveats. But with a modest communication imbalance. Every party still sends big O of m times n, big O of m bits, so it's balanced up to a constant. In fact, all the non-senders send 1.5 m bits. I'm sorry, this should be m. This n shouldn't be here. There's a typo here. Each party sends 1.5 times m bits. So each party sends 1.5 m bits, except for the sender, who sends a constant times m, or the constant is a bit bigger than 1.5. So it's slightly imbalanced, which is kind of bad for the applications I was talking about, but it's good enough but it's helpful for applications that are symmetric, where, say, everybody is broadcasting at the same time. Then balance is not so important in that case. So I'm out of time. Sorry about that, Gilad.
Any questions? Please speak up.
Is it a syntactic question? Would list decoding help?
What decoding?
List decoding. Because you can do list decoding, you can do n minus 1.1 key maybe, and then you can do list decoding and collision resistant caching.
I haven't thought about it, so it's a good avenue to explore. So I just haven't thought about it.
Can you say something about the lower bound? What exactly?
So Thomas, in his original paper, approved a lower bound that says something like if if the number of rounds is 3 in the good case, so it only belongs to a 3-round protocol, and if the communication is just kind of sort of balanced in some very minimalistic way, then you get this 1.5 m n lower bound as both m and n go to infinity in some weird way. But so for large n and for large m relative to n. So yeah, that's it. So yeah. So this protocol down here in our new work is optimal. Okay.
More questions? Okay, let's thank Victor again.
Thank you.
So our last talk is on asymptotically optimal early termination for dishonest majority broadcast, and it will be given by Ivana.
Thanks. Yes, welcome everyone. I'm really excited to share some of the insights of our paper about optimal early termination broadcast. I'm not going to go into too much detail about broadcast because it has been defined very thoroughly before. Just quickly again, we have n players, we have a sender that holds some input, and we basically want the following 3 properties. We want validity, so if the sender is honest, then we want all of the players to output the sender's input. Furthermore, we want agreement, so no matter if the sender is honest or not, we want the honest players to agree on their output. And lastly, we want termination, so we want all players to terminate. So to define the general model we were looking at, so we're looking at deterministic protocols with a complete network, which means we assume every player can communicate with every player over a secure channel. We're looking at the synchronized model, so messages arrive after a fixed time delay, and we're looking at a strongly adaptive rushing adversary, which just means that the adversary can corrupt players on the fly, and it can observe the messages from the honest players before computing and sending its own. So in this model, as has been also said before, there is an upper bound on the number of corruptions that can be handled. If we assume we have no authentication in the information theoretic setting, we actually have an upper bound of n-thirds. But then if we assume we have access to authentication, like signature schemes, we can actually handle any number of corruptions. Furthermore, there is a fairly old result that shows that any broadcast protocol will always have to run for at least t+1 rounds in the worst case, and this is both in the authenticated and not authenticated setting. So with this came the question, well, this is kind of unfortunate because what happens if there is no corruption? Can we do better? So the question here is, can we do better if the number of actually corrupted players F is smaller than the threshold T? To look about this termination, to look at how we can distinguish these types of terminations, Dolev et al. Defined 2 types. They defined simultaneous termination and eventual termination. Simultaneous termination just talks about the fact that all honest players need to terminate in the same round, whereas eventual termination just means they need to eventually terminate. And the unfortunate result is that if we want to have simultaneous termination, then actually this lower bound of t+1 rounds is tight. But the nice thing is, if we assume we're in the setting of eventual termination, we can actually do better. And there we actually have this bound of f+2, or minimum between f+2 and t+1 rounds for any broadcast protocol. Now, this problem has been studied fairly extensively in the setting without authentication. So if we don't have access to any signature schemes, there has been efforts to both preserve the optimal corruption resilience and to preserve the optimal runtime. And a result from Berman et al. In '92 actually gave a first protocol that achieves both optimal runtime and optimal corruption resilience, but at the expense of exponential message complexity. And then 20 years later, Abraham and Dolev actually showed that this can be achieved with polynomial message complexity with optimal runtime and optimal corruption resilience. So looking at this, it might be a bit surprising that the literature in the setting with authentication has been studied less deeply. There has been efforts to look at what happens if we maybe only have half of the corruption, so if it's bounded by n half. And in a recent result from last year, Loss and Nielsen looked or gave the first protocol with any number of corruptions that runs in linear time minimum between f squared and t. And this is where we are building up on, this is where we are contributing, is in this same setting, we're proposing a broadcast protocol that is resilient against t smaller n corruptions that's running in f squared t rounds. Now this might look like it's the same as before. Well, the contribution then actually comes from the fact where we don't assume that we have any number of corruptions, but when we can assume that the number of corruptions is bounded by a constant fraction of the number of players, then we actually have a protocol that runs just in linear time on the actual number of corruptions, which is asymptotically optimal. To maybe quickly show why broadcast with authentication is kind of hard. So we have possible sender behaviors. One option is that the sender sends contradicting messages. This is not really a problem because players can just exchange what they receive, and then because we're using signatures, they can just deduct from this that the sender was dishonest. The problem is what happens if the sender doesn't send a message. So in this case, the first player did receive a message and the second one didn't. Well, the second one can claim that he didn't receive a message, and that's okay. But the problem is that any dishonest player can claim that they didn't receive a message even though they did, and now the first player kind of doesn't know what it means or how to go on. So the way one approach to go about this was presented by Loss and Nielsen last year, and they use this idea called polarizers, and they use it in terms of like a certificate to show or to prove that a sender did not share a message with the player. They define a polarizer to be a tuple of 3 sets, alive, corrupt, and accused, where alive and corrupt are just a partition of the player set into 2 disjoint sets. And then accused is just a set of accusations with the constraint that for any player in the alive set, there needs to be an accusation towards every other player in the corrupt set, but they don't do any constraint on the accusations within either one of the sets. Why is this nice? Well, if we assume accusation soundness, so we assume that honest players never accuse each other, we can actually say that all honest players are always either in the alive or in the corrupt set. And this is nice because if a player receives a polarizer, they can kind of validate its correctness by determining if they're considered alive, if they're considered, or if they're not considered alive by that polarizer. And if they are considered alive in that polarizer, they can kind of accept this certificate this polarizer is given. So to maybe quickly give you an outline, I don't want to repeat their paper, but I think it's valuable to see how they use this idea. So they have this notion of polarizer cast that then it gives the sender the option to share its input with all players, and it gives the honest players a chance to build such a polarizer that actually contains the sender in the corrupt set, so it gives them a proof of the corruption of the sender. And this, they show that this can be done in actually f+2 rounds. Then they use this polarizer cast to build something called graded broadcast with justifiable outputs. So graded broadcast or gradecast is just this notion that we add grades to the output, so how confident are you with, like, how confident is your output? And then justifiable outputs just mean that any output is also accompanied by these proofs, these polarizers, as to why maybe you don't trust an input that you received. And lastly, they use the king phase paradigm to go over different kings, use this graded broadcast to then finally achieve broadcast. Now, this all in all would then result in a runtime of f squared. And then they actually go on to show that this can be capped at t if we're in the setting where f is larger than the square root of t. But for now, this is not that important. So the problem, or the way we wanted to improve upon this, is showing that this first step, building this polarizer, can actually be done faster than in O of f. And we do this by taking this notion of polarizers and just generalizing it. So then we say we don't have 3 sets, we have a tuple of 3 sets and an algorithm. So makeGraph is an algorithm that takes as input a set of accusations, and it outputs an undirected graph on the player set. And now we still have the assumption that the players are divided into 2 disjoint sets, but now we no longer assume that every player in a live needs to accuse any player in corrupt, but we just say that in this graph that has been computed with this makeGraph algorithm, there is no path between any 2 players in a live and in corrupt. If we have this, and we assume again accusation soundness, we also want, again, this property that all honest players are either in a live or in corrupt. So then again, we can use this as a certificate to kind of validate the validity of a polarizer. To maybe give you some idea of context of what this makeGraph algorithm could look like, this is a very simple option. So we're starting off with a complete graph on the player set, and we just remove an edge for any accusation that is part of this accusation set. Now this, if we were to use this makeGraph algorithm in our definition of generalized polarizers, we would actually coincide with the polarizer definition given by Loss and Nielsen, because if we assume that no 2 players are connected, then we know that any player in the live set must have accused every player in the corrupted set. Now this is already a good approach, and this is kind of the approach that Loss and Nielsen did, but we can actually show that it doesn't take into account all of the information that they could, and this is also how we then improve upon the runtime in the step of polarizer cast. So here is an example where we assume we have 7 players, and we assume that the corruption threshold is 4, so at most 4 players are corrupted. And assuming that some player, P6, has this set of accusations, if we were to use the simple makeGraph algorithm, then P6 would compute this graph. And this graph would not constitute a polarizer yet, because in this case, the sender, P star, is still connected to P6. So then this would still be missing accusations to actually get to that point. But what we are arguing is that if we know that the number of corruptions is bounded by 4, we know that in any execution there needs to be at least 3 honest players. And because we assume accusation soundness, or actually we prove accusation soundness in the paper, is we know that honest players will always need to be in a clique of size 3. In this example, generally speaking, there will always be in a clique of size h, where h is the lower bound on the number of honest players. And this is nice because we then know that any edge that is not part of a clique of size 3 cannot be connecting honest players. So in the example, P1 and P3, obviously this edge is not part of a clique of size 3, so we know that this cannot be a connection between honest players, and we argue that we can just remove these edges. And so this is exactly the protocol or the algorithm we propose, or one of them. So we have a click make graph algorithm where it's the same as before. You remove edges based on the accusations, but then on top of that, there is a check or there's an iteration over all of the edges, and we check if there is a click of size h that includes this edge, and if not, we can actually safely remove it. So again, in the example of before, I already argued this, we would then have this as a resulting graph, and this just means that the accusation or the set of accusations that are shown here would give us a valid polarizer for the player P6, and this would constitute a valid certificate in our setting that the sender P star has not shared a message with the player. So why is this useful? Why are we talking about clicks, or why do we want edges to be contained in a click of size h? Well, the reason is that if we have this assumption, we can actually bound the diameter of such a graph by 2n divided by h, where h is again the size of the clicks. And the proof of this is quite simple. So if we assume, again, we have the diameter d, we have some path that has this length, we can look at all of the edges, and because we are in such a click graph, we know that any edge is part of a click of size h. And then furthermore, we can argue that two clicks that are at least like 2 apart will be completely disjoint, because if they wouldn't be, then the path over like that disjoint node would lead to a shorter path, so then this path from V0 to Vd would not be the diameter. And then we can just use a fairly simple counting argument to argue of the size of the clicks, and then we will actually get the bound that we're stating here, that d is bounded by 2n divided by h. And this is actually really, really nice if we go back into the setting of polarizers. So if we assume G is the result of such a make graph execution in the setting where we have a constant fraction of the players, or just a constant fraction is corrupted, then the diameter of such a graph, of this make graph, is going to be constant, and that's just going to be plugging in the result of this lemma with the bound on the number of honest players in any execution. And this is actually nice, because then if the diameter is constant, we argue or we show that a polarizer cast execution is going to run in constant time. So to summarize this, again here, this is the setup that Loss and Nielsen propose, and this is where we improve. So we have a polarizer cast that gives the sender the option to share their input, but if it doesn't, the honest players can construct a polarizer against the sender, and we show that in the setting of the constant fraction corruption, we can do this in constant time. Then I think there's still a typo here, I'm sorry. So then we can use this polarizer cast to build this grade cast, which then will also run in constant time, and then king phase will run over f kings, and then we can actually get to these O of f, this linear time for broadcast. And with this, I would like to thank you for listening. Here are the references in case you're interested, and I'm happy to take any questions.
Thank you. Any questions? Okay. So thank you.
Thanks.